So today's session is about our work across disciplines and across scales, benefiting research for sustainable cities. And on that note, I'm very pleased to introduce the first speaker, Mr. Asahi Kawaura, presenting the database construction of urban geometric parameters with individual building GIS and examination of deep learning algorithms for estimating building parameters. Thank you.
Yes. Hello everyone. Thank you all for coming today. My name is Asahi Kawaura. I'm a master student of Tokyo University of Science in Japan. Today, I would like to talk about database constructions of urban geometry parameters with individual building GIS and examination of deep learning algorithms for estimating building parameters. Recent years, specific climates and weather conditions have occurred in urban areas, such as urban heat island and localized heavy rainfall. One of those factors is aerodynamic and thermal properties due to urban geometry. So, high-rise buildings reduce wind velocity and high-density building distribution increase radiation between buildings. So, to reproduce and assess urban climate correctly, numerical simulation controlling with thermal and aerodynamic properties is necessary. It is possible to consider these properties by incorporating realistic aerothermodynamic parameters, such as roughness length, the displacement height, and sky view factor into the computational grid. These parameters are derived from urban geometry and calculated by 5 building parameters, such as average building height, maximum building height, standard deviation of building heights, plane area index, and frontal area index. Look at this figure. This is the distribution of roughness length of real cities in Japan. Thus, it is ideal to incorporate actual urban geometric distribution into the simulation. But many studies give uniform urban geometric parameters for all computational grids. That's because database of urban geometric parameters over a wide area is still undeveloped. Detailed building data is necessary to calculate urban geometric parameters and available in our limited areas. In view of this current situation, it is necessary to construct the database of urban geometric parameters all over the world. So there are two objects in this study. First, we construct a database of urban geometric parameters using detailed building data in Japan and the US. In Japan and the US, detailed building data is available in 4 areas. Second, for areas no building data exists, we examine a method for estimating plane area index, one of urban geometric parameters, without using detailed building data. We use open satellite data Sentinel-2 and deep learning algorithms based on semantic segmentation. First, I explain how to calculate urban geometric parameters from detailed building data. We use OpenCity model in the US and S3 detailed building data in Japan. Step 1, detailed building data converted from vector data to raster data. Then the grid size is about 1 square kilometer, and it is 30-second latitude and 45-second longitude. The grid size is good for mesoscale simulation. Step 2, 5 building parameters are calculated from raster data. The frontal area index is average value of 8 orientations. Step 3, aerodynamic parameters and thermodynamic parameters are calculated from 5 building parameters. Then we use parameterization by Kanda et al. To calculate aerodynamic parameters and use this Kosho to calculate sky view factor. Now look at this figure. Yeah, this is the distribution of some of urban geometric parameters in Japan and the US. A is plane area index, B is roughness length, C is air area identified with these land use data. Each parameter has high value in warm colors and low value in cold colors. From the result, we can confirm that each parameter has high value in urban area and values of urban geometric parameters are different from ST to ST. Many studies give uniform parameters for all computational grid, but this is not good. This database will be released as open data, anyone to use. I prepare to go public with it now. Next, I explain the examination of deep learning algorithms for estimating plane area index. We use open satellite image Sentinel-2 and deep learning algorithms based on semantic segmentation. Semantic segmentation is a pixel by pixel classification method for images. Look at here. This is the process of calculating plane area index from open satellite images. Input images are Sentinel-2 of blue, green, red, and near-infrared bands. The resolution is 10 meters. The deep learning algorithms in this study include super resolution model and semantic segmentation model. Super resolution model is pixel shuffler and semantic segmentation model is UNet. These deep learning algorithms increase the spatial resolution to 1.25 meter and categorize images into breeding areas and other areas. Finally, plane area index is calculated by dividing the number of breeding pixels in output images by the number of all pixels. We construct this deep learning model by using Sentinel-2 as input data and Plato as target data. Plato is detailed breeding data in Japan. Then we choose low cloud coverage Sentinel-2 images with high solar altitude to avoid shadow and cloud effects. The area of training and validation is Sapporo City and Osaka City and Nagoya City in Japan. The ratio of training to validation is 3 to 1. The test area is 23 watts of Tokyo. This is the example of output images of deep learning algorithms. A is satellite image, B is ground truth, C is output images from deep learning algorithms, D is comparison between ground truth and output. In figure D, white area shows in white area breedings estimated correctly. In red area, breedings are missing estimation. In black area, others are estimated correctly. In blue area, others are missing estimation. From the result, we can confirm that deep learning algorithms can estimate the approximate location of breedings from satellite images. This flex capital plot shows the estimation result of plane area index from the deep learning algorithms. Each plot shows plane area index for 1 square kilometer resolution in Tokyo in Japan. Horizontal axis is ground truth and vertical axis is estimated plane area index. The RMC is 0.074. From the result, the deep learning algorithms is confirmed to have certain estimation accuracy, but they are trends to underestimate in areas with high value of ground truth and overestimate in areas with low value of ground truth. In this slide, I discussed the factors of underestimation from relationships between IOU and breeding sites in satellite images. IOU is accuracy matrix used for object detection. IOU close to 0 indicates bad accuracy and close to 1 indicates good accuracy. This scatter approach shows relationships between IOU and breeding size and number of breedings in satellite images. Horizontal axis is breeding size and vertical axis is IOU, and the color bar shows number of breedings in one grid. The targets are grids with plane area index of 0.4 or higher in Tokyo. From the result, IOU tends to decrease as the number of breedings increases and the average breeding size decreases. This result shows if learning algorithms can capture detailed and high-density breedings, it means low resolution affects accuracy. This is summary and conclusion. We construct a database of urban geometric parameters using detailed breeding data for Japan and the US. The database constructed in this study is expected to be used for mesoscale simulation. We examine deep learning algorithms for estimating plane area index using Open Satellite Data Center 2. The usefulness of the method was demonstrated, but the low resolution of satellite images affected the accuracy. In recent years, open breeding data is increasing, so it is expected to expand the database of urban geometric parameters. Thank you for kind attention.
That's great. Do we have any questions? Yes, Alan.
Very interesting work. Just a simple question. In your predictors, you use a sentinel. Why have you tried exploring the other bands of sentinel as predictors? Why you select? Yes.
Because in Sentinel-2, the spatial resolution parameter is only blue, green, red, and near infrared. The spatial resolution is very cold, so we choose the most. We choose this band. Okay.
One more. I might just ask, how difficult do you think it will be to expand outside of Japan and North America? Are there any constraints, seeing that you're relying on Sentinel-2?
No.
Or you think it's easy to expand to any other area?
I think it is difficult to expand as areas because detailed breeding data is not exist. But recently years, Microsoft or ML breeding brains expand, so I want to use it.
Thank you.
Thank you.